So dimensional analysis was introduced in the previous lesson. That previous lesson also talked a lot about dimensionless numbers, things like the Reynolds number and Froude number. Those are going to be important when we do dimensional analysis. So what we're going to do is we're going to try to reduce the number of variables in the problem, and the way we're going to do that is through those dimensionless numbers that we saw previously. So the best way to see how to do this procedure is through an example. So let's say we want to know how the drag force on an object, in this case a sphere, depends on all the other flow parameters. So I have a sphere moving in a fluid. It's moving at a certain velocity, has a certain size or diameter. The fluid has a certain density, has a certain viscosity. So you can see if you change all these things, if the sphere moves faster, that's going to change the drag force. If I have a different density of fluid, that might change the drag force. Things moving in air might be easier than moving in water, for example. But I want to know how all these variables affect the drag force. And so in general, there are three ways to solve a problem where you don't know what to do. So first option that we've been doing for pretty much this entire course is what's called analytically, using math, using equations. So you plug numbers into an equation to find the answer. That's great if you know the equation, but we don't actually know the equation for the drag force of a sphere yet. We'll actually get to it in a few weeks. But for now, we don't actually know what it is. So using equations is kind of out the window. So what are the two other methods? Well, first method is numerically, so you can actually run some computer simulations. Again, that's kind of beyond this course. The last thing you can do is do experiments. So take a bunch of spheres, go down to a lab, get some water, some other fluids, and basically want to vary, so have different size spheres, different diameters, have different velocity of fluids moving across them, change the density of the fluids. We want different fluids, want some air, want some water, want some other things. And so basically what you're going to do is run a whole bunch of experiments where you keep the same fluid and then change other parameters, then keep the same sphere, change other parameters. So that's going to take a really long time because you basically have to change one thing at a time and then vary all the other ones and see what happens. And so this is where dimensional analysis really helps, because instead of having to change 4 different things independently, well, the point of dimensional analysis is to reduce the number of variables. So instead of this case, I have actually 5 variables. The one you're looking for counts, so force plus these 4 things it depends on, 5 variables. I want to reduce that to a smaller number, 2 or 3, and then when I do my experiments, I want to vary 1 or 2 things as opposed to varying 4. So that's where dimensional analysis really helps. So the first step is to actually identify all the variables in the problem. So basically for my drag in the sphere example, I want to know the drag force. What could drag force possibly depend on? If the size of the object changes, depend on that. Velocity changes, could depend on that. Density of fluid, viscosity of fluid. So those are things that the drag force could possibly depend on. There might be more depending on the problem, might be less, again, depending on what you're looking at. But that's what you want to do, kind of think about, here's what I want, what are the things you have to depend on, and those are my variables for my problem. Then you also want to identify the dimension of each of these variables. So again, previous lesson showed the dimensions of all these common variables in fluids. So diameter, obviously dimensions of length, velocity, length over time, meters per second, density, mass per length cubed, viscosity, meters over length into time, and then force, mass times length over time squared. Again, force in newtons. Newtons the same thing as the kilogram meter per second squared. So kilogram meter per second squared. So those are my variables and their dimensions. So remember, the point of dimensional analysis is to reduce the number of variables. So what we're going to do is start with my original number of variables, 5, and reduce that down to 2 or 3. And those 2 or 3 variables are going to be these dimensionless numbers we talked about before. So what I want to know now in step 2 is, I'm starting with a certain number of variables. How many variables am I going to be able to reduce that to? So for my current example, I'm starting out with 5 things. Am I going to reduce that to 2 things or 3 things? What's the exact number there? And so the way to figure that out is something called the Buckingham Pi theorem. So these dimensionless numbers, these dimensionless groups that we end up with at the end of this are called pi groups. It's another name for them. So the number of pi groups we're going to get from any dimensional analysis. Number of independent dimensionless groups is given by m minus n. So m is the number of variables in my problem, n is the number of dimensions. So for my current situation, the drag on the sphere, we saw we had 5 variables, including the drag force, what we wanted to have, so make sure you include that. So m in that case was 5. N, the number of dimensions we have in the previous step, we saw we had dimensions of length, we had dimensions of mass, and we had dimensions of time. So 3 dimensions there. So what we're going to end up with for my 5 variables is 2 pi groups. So I should end up with 2 variables essentially, those variables being dimensionless numbers. So hopefully by the end of this procedure, that's what I'll have. Now that we know how many variables or pi groups we're looking for at the end of this, third step is to set up a table. So my table is going to have n plus 1 columns. So if you have 3 dimensions like we do here, we have 4 columns. My first column is basically what I did in step 1, have all my variables and all their dimensions. And then I have m number of rows, so each row corresponds to one of my variables. I'm not counting the header row. And so that's step 3, set up that table. The next step is to actually start eliminating variables. And the way we're going to do this is pick a dimension to eliminate. So I have length, time, and mass. I want to get rid of one of those. Doesn't really matter which one you start with. End of the day, there are easier ones and harder ones though. Mass will be hard to deal with. Time's not that easy to deal with either. The problem with mass and time is that they involve other dimensions as well. So every variable I have here, everything with a mass in it, also involves a length and or time. The time also involves a length and or mass. So length is the easiest guy to eliminate. So that's what I'm going to do, kind of show you the procedure. So I'm going to eliminate length, and now I also want to choose a variable to eliminate length with. Again, length is everywhere. Every one of my 5 variables has a length in it, so I can use any variable that I want. But again, if I use velocity, for example, when I eliminate length, a bunch of weird things are going to happen with time because they're dependent on each other. So this, again, is the easiest one to deal with. So I'm going to eliminate length using the diameter. And so what I mean by eliminate is basically get rid of all the lengths. So to get rid of a length, I want to divide by length. So this guy is going to be divided by length, or in other words, this velocity is going to be divided by my diameter. This guy has a length cubed on the bottom, so to get rid of length cubed, I want to multiply by length cubed, because that way length cubed is going to cancel out. So in other words, I want to multiply density by diameter cubed. That's going to get rid of my dimensions of length. Same deal here. I'm going to multiply this guy by diameter, get rid of the length on the bottom. Force, I'm going to divide by length to get rid of the length on top. So what I end up with when I do that, so diameter, d, is what I'm actually using to eliminate things. So him divided by himself just gives me nothing. So that guy basically gets crossed out. Then as I said, velocity divided by diameter now gives me units of 1 over time. So this variable combination has units of 1 over seconds. Rho d cubed has a unit of a mass. That's basically density times volume, which we know is mass, so that makes sense. Viscosity times diameter is mass over time, and force over diameter is mass over time squared. And then last step is to repeat what we just did till all variables are dimensionless. So now, if I did step 4 correctly, all my lengths should be gone, which they are. So all I have now in terms of dimensions are mass and time. So now I want to pick one of those to eliminate, and whatever I do, that's going to go to the next column. Then I'll be left with the other one. So at that point, I'll do that, and then I'll end up with my last column. And once I get to the last column, I should have those 2 dimensionless numbers that I'm looking for. So now here, I have a choice. I can eliminate either time or mass. It doesn't really matter which one I want to do. But again, if I look at this, the 2 easy ones will be these 2, because if I want to eliminate time, this guy only has time in him, so he'd be a good candidate to eliminate time. This guy only has mass in him, so he'd be a good candidate to eliminate mass. Again, it doesn't matter which one you want to do. So just to be different and do it a bit of a harder way, I'm going to eliminate mass using this guy here. So this guy has a mass on top, so to get rid of mass, I'm going to divide by him. But again, the problem when I do this, as you're going to see, is that when I divide by mass, I'm also going to be dividing by 1 over time or multiplying by time. So that's going to mess up some other things. So we'll see why that's harder than the previous one. So doing this, so dividing by mu d, get rid of mass. The first one doesn't actually have a mass, so I don't need to do anything. So v over d just stays v over d, still units 1 over time. So divide this guy by units of mass. So divide him by mu d. I have rho d cubed over mu d. One of those d's cancels out. So I have rho d squared over mu. That gets rid of this mass. But when I divide by this guy, I'm dividing by 1 over t. So divide by 1 over t when there's t at the top. So this guy has units of time. Again, you can verify that if you want. Think of density, kilograms per cubic meter times meter squared divided by viscosity, kilograms per meter second, and that should all work out to seconds. Again, this guy's the one I used to eliminate it, so he's gone. And then this guy, I want to get rid of mass again, so divide by mu d. I have f over mu d squared. Again, that gets rid of my mass, but it brings the time to the top. So I have time over time squared, which is 1 over time. So now if I did everything right, all my masses should be gone, left with just times, so just t's over there. And now repeat this again, so get rid of all my t's. Again, I'm going to do this the easy way. Rho d squared over mu is t, so I'm trying to use that to get rid of t wherever I need to. So what I have is a 1 over time. If I multiply that by t, I'll get rid of it. Another 1 over time, so multiply that by t, I'll get rid of it. So it's basically multiply this guy by rho d squared over mu, multiply that guy by rho d squared over mu. Again, doing that, I use this guy, so line goes over there. Multiply, I get rho vd over mu. And then multiply this guy down here. The d squared cancels out. I get rho f over mu squared. Now, again, those guys should be dimensionless. Again, good thing to do is plug in actual dimensions to make sure they're dimensionless. So plug in all your dimensions, make sure they all cancel out, make sure they are dimensionless numbers. As long as they're dimensionless numbers and you have the right number of them, remember we're looking for 2. Exactly what we have is 2. As long as that happens, you have the right answer. Now, there are more than one version of the right answer. So for example, you can see this guy, rho vd over mu, that's the Reynolds number. You may recognize that guy. This guy down here though, you don't recognize that guy because he's not in the list that we gave previously. So these two answers are not unique, depending on the way that you did this. So what variable you chose to eliminate and what what dimension you chose to eliminate and what variable you chose to eliminate that with is going to give you different answers. So if I did this a different way, I could have ended up with, say, mu over rho vd and f over rho v squared d squared. Those should have been my 2 at the very end. So it looks like a different answer, but it's actually the same answer because we're looking for 2 groups. But if you remember what the Buckingham pi theorem said, is that at 2 independent groups. So if I have 2 independent groups, it means I can't make one from the other. So this guy and that guy would not be a good set of 2 because one is just the other one upside down. So those are not independent. I can actually make this guy out of these 2 if I took this guy and divided him by that guy squared. So I'm dealing with dimensionless numbers. Doesn't matter what I do to them. I can multiply them together, divide them, square them. They're still going to be dimensionless. So I can take this guy, multiply him, or divide him by this guy squared, and doing that, that's exactly what I get. So again, it doesn't really matter what you get at the end of this, as long as it's the right number and they're dimensionless. That's all you need. So how does this all help us? Again, we know the point of this was to reduce the number of variables. So we reduced the number of variables in our problem from 5 to 2, but how does that actually help? So the point of this problem was to find the drag force on a sphere. So how do we find the drag force on a sphere from our previous results? So the point of dimensional analysis is that once we get our pi groups are related through some functional relationship. So one pi group is a function of all the other ones. So in our case, what we have is one pi group. I'm going to choose rho f over mu squared because I'm actually looking for the drag force f. So the one with f in it is the one I want to put over here. It's some function of all the other ones. In this case, I only have one other one, and that's rho vd over mu. So if I actually wanted to find my force f, it's mu squared over rho, some unknown function of rho Vd over mu of the Reynolds number. Now this still not going to tell me what the drag force is because I don't know what my function f is. So how did this actually help? So if you remember, before we did dimensional analysis, I had a problem where I wanted to know what the force was, and I knew it depended on these four things. So I started with force is some unknown function. I'm going to call it f1 because it's different than this function down here. So f1, some unknown function of all these variables. If I want to know what this unknown function is, the way I was going to do that was experimentally. So you go down into the lab and go down there, get a whole bunch of different diameter spheres, and then run a whole bunch of experiments on these different diameter spheres to figure out how it depended on d. Run a whole bunch of different tests on different velocities, find out how it depended on v. Same thing for density, same thing for viscosity. That's a whole lot of different tests. What I have now, on the other hand, is my force is mu squared over rho, again some unknown function, but this unknown function is only of one variable, namely the Reynolds number, which is that combination rho Vd over mu. So really in this case, all I need to do is vary one thing, the Reynolds number. I can do that any way I want, vary any one of those four numbers to change this number, then run a bunch of experiments just changing this one number, get a bunch of measurements for that, and that gives me this function f, and from that I can find my drag force. So basically cut my effort down by a factor of 4, instead of varying 4 things, only varying one thing, save a lot of time, save a lot of money.